maximum and minimum. Most macroeconomic analysis concerns finding the maximum or minimum of a function. For example, a consumer chooses a bundle of goods to maximize utility, or a firm chooses inputs to minimize costs. The problems of finding a maximum and finding a minimum may sound as though they are very different, but they are similar mathematically. We think of the problems of finding either maxima or minima as special cases of the more general problem of finding extrema. Mathematicians and economists are sometimes interested in the local properties of a function, or equivalently, the properties of a function within the neighborhood of a point x. A local property is one that holds within a neighborhood of x, that is, within some positive but possibly very small distance, epsilon is greater than 0. From the point x. For example, a function has a local maximum at x star if there exists an epsilon greater than 0 such that f of x star is greater than f of x for all elements of x, such that x is an element of open parentheses x star minus epsilon, comma x star plus epsilon, that is in the neighborhood of x star. A local extremum of a function f of x is either a local minimum or a local maximum of the function f. If we move from the local extremum at x by an amount less than epsilon, the value of the function becomes less extreme. Figure A dot 4 graphs the function f of x equals x times the sine of 6 pi x, which has many peaks and troughs. All the local extrema are indicated with bullets. Points A, B, and C are local maxima, while points C, D, and E are local minima. All these local maxima and local minima together compose the set of local extrema. Point A is a local maximum because if we either increase or decrease x just a little, the value of f of x decreases. Similarly, D is a local minimum because if we either increase or decrease x slightly, the value of f of x increases. Global extrema. The global maximum, usually called the maximum, is the largest maximum, and the global minimum, or minimum, is the smallest local minimum. In figure A dot 4, the global maximum is point C, and the global minimum is point F. If there are two local maxima that are both equally large and larger than all other points, we would say that there are two global maxima. Figure A dot 4, the illustration of local and global extrema. On the vertical axis, we have f of x, and the horizontal, we have x. And starts at the origin, goes up, and then goes down below the x line. It's a squiggly up and down line. The bullets indicate the local extrema. Point C is the global maximum, and point F is the global minimum. We have figure A.5, illustration of the extreme value theorem. According to the extreme value theorem, if a function is continuous and defined on the closed interval, it contains at least one minimum and at least one maximum. This continuous function has a maximum at a point A and a minimum at point B. This A is unique minimum and maximum. Figure B is many minima and maxima. This continuous function has an infinite number of maxima and minima that equal 1. C, unique maximum, no minimum. This function is discontinuous at the point marked with a hollow point. So the theorem cannot be used to draw inferences about the existence of minima and maxima for the domain open parentheses 0, 1, close bracket. The function has a maximum but no minimum. D, many maxima and minima. This discontinuous function has infinite maxima and minima. Existence of extrema. In economics, we often want to know if a function has a maximum or a minimum in the relevant domain. For example, we might examine whether there is a minimum for a function f colon open bracket 0, 1, close bracket yields all real numbers. That is, f takes values from the interval between 0 and 1 inclusive and maps them into the real line. Not all such functions have a maximum or a minimum. Continuity of a function is a sufficient condition for the existence of both a maximum and a minimum. This result is a consequence of the extreme value theorem. If the function f is continuous and defined on the closed interval open bracket a comma b close bracket, there is at least one c in open bracket a comma b close bracket such that f of c is greater than or equal to f of x for all x in open bracket a comma b close bracket, and there is at least one d in open bracket a comma b close bracket such that f of d is less than or equal to f of x. For all x in open bracket a comma b close bracket, functions that are not continuous might have minima and maxima, but there's no guarantee. Figure A.5 illustrates several possibilities. Panel A shows a continuous function. Y equals f of x equals 24x minus 75x squared plus 50x cubed, with a single minimum and a single local and global maximum in open bracket 0, 1 close bracket. In panel B, the continuous function y equals f of x equals 1 has an infinite maximum in open bracket 0, 1 close bracket. In panel B, the continuous function y equals f of x equals 1 has an infinite number of maxima and minima in open bracket 0, 1 close bracket. In panel C, the discontinuity in the function y equals a set of two lines. The first line, 24x minus 75x squared plus 50x cubed, where x is less than 0.8. The second line in this set is 24x minus 75x squared plus 50x cubed, where x is greater than 0.8, is shown as a hollow circle. Because of this missing point, there is a unique maximum, but there isn't a global minimum with open bracket 0, 1 close bracket. Finally, the discontinuous function plotted in panel D, y equals a set 0, a set of 2, and the first set is 0, where x is less than 0.8, and the second set is 1, where x is greater than or equal to 0.8, has an infinite number of maxima and minima in open bracket 0, 1 close bracket.